Okay, Wednesday back here, Physics 1151. We're here for our final lecture of Chapter 29 and our final lecture of Unit 3. This is the last bit of material that will be on the exam. So today we're going to cover, final topic is just the force and a torque on a current loop, and this has an application to DC motors, which we'll get into. This lecture will be a little bit shorter because the last two, Monday and Tuesday, were pretty long. So this will be it for today. Today will be about 20-25 minutes. So quick review, we're going to do a quick review of a single current loop, which is a magnetic dipole, the magnetic field, and then we will get into the force and a torque on the current loop, and then the application to a DC motor. So remember, exam 3 is Monday in class, covers chapters 27 through 29. So this is the last lecture of that unit. And reminder, homework 11 is due Sunday morning. Okay. So a couple lectures ago, we talked about a current loop, a loop of wire that has current running through it. And this is what's called a magnetic dipole. And we define this quantity called the magnetic dipole moment, and we give it the symbol mu. That looks like a U. And the magnitude of the dipole moment is equal to the area of the loop, so it's pi r squared if it's a circle, where r is the radius, multiplied by the current. And the direction of the magnetic dipole is if you take your hand and you rotate your fingers of the right hand in the direction of the current, which in this case is counterclockwise, your thumb will point in the direction of the dipole moment. And the magnetic field produced by this dipole is along the axis pointed to by the dipole moment. Okay. So in this case here, if we were to calculate the magnetic field at all points, it looks just like the electric dipole, remember? And also just like a permanent bar magnet. And so here, if you look at the white just as a bar magnet, the field lines come out of the North Pole, they curl around, and they emerge back into the South Pole. Okay. If we look at the dipole moment, the direction of the dipole moment, which in this case, if you curl your hands in the direction of the current points to the right, the magnetic field lines are coming out along the direction of the dipole moment. They're forming circular loops, and they come back. And so this side of the loop in which the field lines are emerging from is exactly like the North Pole of a bar magnet, and the side of the loop in which the field lines are going back through again is like the south side. And so this forms what's called an electromagnet, right? And so to get the direction of the North Pole and the South Pole of this current loop, we need to find out what the direction is of the dipole moment, and that's the direction, that's the side of the loop that the North Pole is on of the magnet. And so these current loops can exert forces on one another just like bar magnets can. So the current loop creates a field. Now the current loop, if you place it in a field produced by other charges, like you put it between two poles of a bar magnet, the North Pole and a South Pole, the magnetic field, it also can experience a torque. Okay, so to see this, here's our loop, and let's suppose that we run wire in this direction. Okay, so if you look at the left-hand side of the loop, we want to get the direction of the force. Okay, and if you look, here's a top view of this. So here's the current coming out of the screen toward you, and on the other side of the loop, the current is coming in. So this is side 1, which is over here, and this is side 2. So if you apply the right-hand rule, and remember, it's IL cross B is the force. So we take our hand and we point it in the direction of the current, which is upward in the page, and our palm points in the direction of the magnetic field, so the palm will point from left to right, and our thumb gives us the direction of the force, and so the force in this case is going into the page, or into the screen. Similarly, at point 2, you can apply the right-hand rule, and you get the force on this segment of the wire, and that is coming out of the screen. And so, if you look at the two forces on the sides of the loop, they balance, they cancel. So there's no net force on the loop. So then what's going on? Why is the loop moving? Well, if you look there's a torque on the loop. So here's the force trying to pull this side upward, and here's the force trying to pull this side downward, and the net effect is to rotate this plane of this loop, and that exerts a net torque which tends to rotate the loop. So the net force is 0 on the loop if you place it in a field. There's no net force, but there is a net torque, okay? And that will tend to rotate the loop clockwise, okay? So what we want to do next is we want to get a mathematical expression for the torque on this loop, because it's useful for explaining how DC motors work. And so what we'll do first is, here we're looking down on the loop, and here comes the current out of the screen here, and here comes the current into the screen here. And so if you, again, the right-hand rule, you get that the force is horizontal here and upward, and here the force is downward, and so it's going to rotate the loop clockwise. Now at this point, we get a maximum torque, and the question is why? Well, it's rotating about an axis into the page, into the screen, and so remember the torque from 1150 is equal to R cross F. It's the moment arm times F. And when the moment arm R is perpendicular to F, you tend to get maximum torque. So here we get maximum torque when the normal to the loop, which is the direction of the dipole moment, is perpendicular to the field. Okay? Now you rotate this loop 90 degrees, and at this point, you get 0 torque. And the question is why? Well, the force is along the same direction as the moment arm, right? So there's no net torque. Okay, they're parallel. And so at this point, you get minimum torque. So the torque is maximum when the dipole moment direction is perpendicular to the field. Okay? And so mathematically, we can go through and you can get the torque, and you get the torque as the force times the moment arm. And the force is IL cross B, and since current and the magnetic field are perpendicular, it's ILB sine of the angle between, which is 90 degrees. So the force is ILB, and the moment arm, in this case, is 1/2 of the width times the sine of the angle between the magnetic field and the normal to the loop, which is the dipole moment. Okay, so that's the force on this side, and then the same torque is on the other side, and when you add them up, you get that the torque is I, and then times W, which is the width, and L, which is the length, and length times width is just the area of the loop, so that's I times the area of the loop times B times sine of theta. So that's the magnitude of the loop, of the torque. And the torque is strongest when the angle phi is 90, which means that the dipole moment is perpendicular to the field. Okay, well, this is just the equation for the cross product, remember? And so the cross product is just the magnitude of the first vector, which is the magnetic dipole moment, current times area, times the second vector, which is B times sine of phi, and we can write that as the torque is the cross product of the dipole moment with the magnetic field. Okay, so that's our equation for the torque on the loop. So let's do an example here. So suppose that you have the coil has an area of 2.0 times 10 to the negative fourth meters squared. And suppose that we want to get a bigger dipole moment, so we have 100 loops, okay? And it turns out if you have 100 loops, basically the area is 100 times that of a single loop. So your dipole moment's 100 times greater. Okay, don't worry about this on an exam. We're not going to deal with n loops on an exam for this. But it's n times greater. Okay, so first we're going to calculate the dipole moment. Okay, so if we know the current and we know the area, we get the dipole moment for each loop, and then we multiply 100 because we have 100 loops. So now we get 9.0 times 10 to the negative 4 amps meters squared as the dipole moment. Okay. If we want to find the maximum torque that the field exerts on the loop, the maximum torque is when the angle is 90 degrees. So we set sine of 90 to 1. And we plug in the magnetic field, it's 0.15 Tesla, and we multiply that by the dipole moment, and we get the maximum torque is 1.4 times 10 to the negative 4 meters. Okay. So the main point of all this is that you're able to use the equation which relates the torque to the dipole moment in the magnetic field. Okay. And to do this, to get the direction right, you have to get the dipole moment's direction right, which means in this case, you take the current and you curl your hands in the direction of the current, and the dipole moment is the direction of your thumb. So in this case, it's going into the page. And if we know the direction of the dipole moment and we know the direction of the field, then we can get the torque. The direction of the torque. So here's an example of what happens when you put a current loop and you put it inside a magnetic field. So you put it between the poles of a magnet, and we're going to run a current through it, and that is going to cause a torque which is going to get the loop to rotate on this shaft. And that in turn, in this case, if this is a CD player, that will get that to rotate. Okay, so now we've just made a simple DC motor. So let's go into how this works here, and then we'll show you a YouTube video. So in this case, here's the current going through, and here's the potential, which is running current through. And here's the positive side, and you've got a slip ring here, right? And you see they're separated by an air gap. So this side here of the brush is connected to this side of the armature here, and this is always connected to the positive side. So the current is going to run through here, and that's going to exert a force on this side, which is downward, and on this side, which is upward, which is going to rotate the loop. Okay, now the problem is when you rotate it 1/2 of turn, so now this downward side is up and up is down. If the current through each side is in the same direction, then when this side here is up on the left, you're going to get a downward force. And when this side that is formerly on top is down here, you're going to get an upward force, and it's going to rotate it in the opposite direction. And then when the loop goes through another half, it'll rotate back to the original, and then the opposite. And the net effect is that instead of continuing to turn this motor, it'll just keep going back and forth, so it won't turn. So what we need to do then is we need to reverse the direction of the current every half cycle so that whatever side of the wire is up here, the current through that side is always going downward, and whatever side of the wire is down here, the current through that side always has to go upward, so that you get these force directions to stay the same, and that will cause the loop to continue to rotate in the same direction. And so what that requires here is for this, as you go through, and you got this brush here with these rings, that requires that the current in each side has to change directions every half turn. So whatever side is always connected to this brush right here will always be connected to the positive terminal. That will always have current in this direction. And whatever side is connected to this brush, the current will always be flowing downward. And so this has to continue to rotate, and it makes and breaks contact, the rings do, with this brush, and the net effect is that the current in this side will always go downward, and the current here will always go upward, and you will continue to have this torque in the same direction. And so we're going to end this chapter with a nice YouTube video. It's about 10 minutes on with how the electric motor works.
If you look around your house, you will see a professional who wants to keep their skills sharp. Sign up for free by going to brilliant.org/Jared Owen. The first 200 people will also get 20% off their annual premium membership.
Getting a call or message from one phone to another is surprisingly complicated.
And this electric cutting knife. But how does the electric motor work? You turn it on and somehow it starts rotating. Why is that? In this video, we'll cover the basics of electricity and magnets, and then put it all together to understand how the motor works. This video is sponsored by Brilliant. Let's start with something called a circuit. You have a battery, some wires, and a device that uses electricity such as a light bulb. Electricity flows through the circuit. But as soon as there is a break in the wire, the electricity stops flowing and the light bulb goes off. The path must be complete for the circuit to work. This is best done through the use of a switch. Electricity is flowing down the wire. This is called conventional flow. If we take the battery out and flip it, then the current will flow the other way. The light bulb will still work in either case, but there are some devices that will work differently depending on which way the current flows. Okay, so that's the basics of a circuit. Now let's come over here. This is a magnet. It has a north pole and a south pole, and it likes to attract other metal objects like these paper clips. If you bring another magnet towards it, opposite poles attract, and the same poles repel. The magnets don't have to be in this shape. For example, some magnets might be more flat like this. You can think of this magnet as always on. It's always working. You can't really turn it off. That's why it's sometimes called a permanent magnet. It's made up of many smaller magnetic domains that are lined up in the same direction. But later, I'll show you a type of magnet where this is not always the case. Let's take one of our permanent magnets and drill a hole in the center and put it on something that will allow it to spin. Now bring another magnet towards it. Our spinning magnet will immediately line up until opposite poles are right next to each other. Now switch out the side magnet. The same poles repel and opposite poles attract. If we keep switching out these side magnets, then our spinning magnet will just keep spinning. This concept of the spinning magnet is really important. We'll come back to it in a moment. Here's a metal bulb, which is not a magnet. It's made up of magnetic domains, but they are pointing in random directions. Now let's take a wire, wrap it around several times, and then create a circuit. The current through the wires forces the magnetic domains to line up. That means we've just made a magnet, or more specifically, an electromagnet. It can do the same things that a permanent magnet can. It can pick up pieces of metal, and it has a north and a south pole which will attract or repel other magnets. But the electromagnet is special in the sense that it can be turned on or off, just like the light bulb. You can't do that with a permanent magnet. Now watch what happens when we flip the battery. The electric current was flowing this way, but now it flows the other way. This will cause the poles on our magnet to switch places. North will become south, and south will become north. This is called reversing the polarity of an electromagnet. Instead of flipping the battery, an easier way to do this is to just switch the wires. You should be aware that the electromagnet will get very hot if it's on for a while. Just a caution in case this video inspires any science projects. Let's come back to our spinning magnet. This time we'll replace the spinning magnet with our electromagnet. As soon as we connect the wires, the magnet turns on and it lines up with the side magnet. Now, in reality, connecting these wires would prevent the bolt from spinning freely, but what's important here is the concept of the spinning electromagnet. Now let's switch the wires to reverse the poles on the electromagnet. The same poles repel and opposite poles attract. Now reverse the polarity again. Same poles repel and opposite poles attract. If we keep switching the polarity, our electromagnet will just keep spinning. To make this stronger, let's bring in another permanent magnet on the side. Notice how this side has the south pole towards the center, and this side has the north pole towards the center. The side magnets work together to spin the one in the middle. This right here shows the very basics of an electric motor, but we need to make a few improvements. The two side magnets can be replaced with stronger curved magnets. And instead of a bolt with wires, we're going to use a metal loop. This is called the armature. Connect our wires and we have a circuit again. This time you can think of the electromagnet as flat like this with the south pole pointing up. Now the armature will spin until opposite poles are lined up. We can keep it spinning by switching the wires just like we did before. But this is a lot of work to sit here and manually switch these wires. We need to add something to the armature called a commutator. It's a ring with gaps on the opposite sides. The commutator will spin along with the armature. Now we connect the circuit with two brushes on the side. These brushes will slide along as the commutator spins, and they are spring-loaded so that they always maintain contact. The current flows from the wire, through the brush, the commutator ring, the armature loop, and back through the other side. Now we have our electromagnet and the armature spins. As we come around this time, the brushes will switch contact to the other side of the commutator ring. Remember, there's two brushes, so this is happening on both sides. Before the switch, the current in the armature is flowing this way. After the brushes switch sides, current will flow the other way. This means the electromagnet switches polarity, which will cause the armature to keep spinning. This commutator ring does the same thing as switching the wires like we were doing before, but this time it does it all on its own. It will continue to spin as long as we're connected to a battery. Disconnect the battery, no more electromagnet, and the spinning stops. Now so far we've only used one loop on the armature. This will cause our motor to have an irregular speed, and in fact, we could get stuck in this position, with the brushes halfway between commutator segments. What we can do is split the commutator ring and then add another loop. So first, the brushes are in contact with these two commutator segments, which turns on this electromagnet, which causes it to start spinning. Once we get to here, the brushes switch contact to the next pair of commutator segments, which means this loop turns off and the next loop turns on. Now this electromagnet wants to spin. The brushes switch contact and the next loop turns on. This keeps happening as our motor spins. It's almost like the loops will take turns being an electromagnet. Some electric motors will add many loops to the armature. This ensures that there will be a continuous spinning motion on the motor. This spinning force on the armature is called a torque. Stronger torque means a faster spin. There are some things we can do to improve the torque of the motor. Electromagnets are stronger when there are more wires. This is true when we wrap more wires around the metal bolt, and it's also true when each of our armature loops are made of many wires. The motor will have stronger electromagnets, which means it will spin faster. If you look at some pictures of real electric motors, you can see lots of wires wrapped around. And yes, this is the same reason. More wires wrapped around means stronger electromagnets. Another way to make this stronger is to use more electricity. Let's learn a few more terms here. The part that doesn't move is called the stator. In this case, it's the two permanent magnets on the side. These fit inside the edges of the motor case. The armature in the middle is also called a rotor. Remember, this is the part that spins. The axle goes through the middle here and then sticks out the back of the motor. What I've shown you in this video is called a DC motor. If you have a device that moves and is powered by a battery, there's a good chance there's a DC motor in it. Other types of electric motors will work a little differently than what I've shown here. No matter the type of motor, most of them will produce some type of spinning motion. Once it's spinning, we can use this to make different devices move. In this case, a kid's toy. Or even a fan that cools your room. The spinning of the motor can be converted to other types of movement, such as the side-to-side motion that we see in this fan. Or how about this electric cutting knife? Each blade is going back and forth. It all starts with the spinning of the motor to turn a gear, which then pushes these two pieces back and forth. So hopefully this video has made a few light bulbs go off in your brain. If you like learning new things, head on over to Brilliant.